Okay, hey guys, this is the homework videos for tutorial 6. This is your first homework assignment using virtual work. So a few words on virtual work. So usually we use the word virtual to imply something that does not actually exist, right? And so virtual work in this case is referring to the fact that we're applying a virtual force or force that, so we have this, for example, we have 400 kilonewton, 100 kilonewton, 300 kilonewton forces. We're going to apply a virtual force that is minuscule compared to these forces. And that will not affect our overall system, but it'll allow us to calculate deflections. Unfortunately, although we're using a virtual force, it is not a virtual amount of work. Virtual work is one of the most time-consuming methods to use in structural engineering, but the advantage of it is that it's the most flexible. With virtual work, you can solve just about any problem that pops up, but in exchange for that flexibility, you have to do a very rigorous analysis. I will say that virtual work is, although it is tedious and it is long, it is not particularly complicated. So once you're able to get the hang of doing a couple virtual work problems, all the other ones are going to be very similar. But because it is very tedious and very long, there's a lot of room for mistakes. So when you're going through this, just be careful and don't rush it. This takes a lot of time. There's no fast way of going through it, and it's good to get a couple of these down by hand to make sure you can do well on the exam. So for virtual work, you always solve your problem by breaking it up into two systems, a P system and a Q system. So with the P system, you want to find the internal forces due to all your members, due to all your external forces. So for example, in this case, I would find the tension or compression, I would find the axial force for every single one of these members, just due to my original 3 loads. I don't care about what my deflections are just yet. I don't care about my virtual force. I just want to find all the internal forces due to all 3 of these loads. So this is the P system is due to original loads. My Q system, on the other hand, is based on a unit load, is the forces due to a unit load or a virtual load, and I apply that at the point I'm interested in. So say, for example, in this case, I'm interested in the horizontal displacement of joint C. I would apply a unit load at joint C. And what do I mean by unit load? So due to virtual loads. What I mean by a unit load is just if I'm going to draw my diagram out here, for example, and I have something that looks like this. I was interested in the horizontal displacement at point C. So I put a point load at C in the horizontal direction. That is my virtual load. So I have my internal forces now. So as you can see, like already, I've had to do 2 complete truss analyses for a single problem. In this case, in the P case, I found the internal forces due to all 3 of these loads. In the Q case, I found the internal forces due to a single unit load. All right. So as you can see here, there's a lot of things to keep track of. For virtual work, you almost always make a table. So I'll have member here, for example, and then I'll have my FP, my FQ, my L, my A times E, and then I'll have it all together, FP, FQ times L on AE. All right, so I'll have some sort of table that looks like this. And this would be, so for example, in my problem 1, I have 1, 2, 3, 4, 5 members. I would have A, B, B, C, C, D, B, D, and AD. And I would find the force, for example, due to AB, or in force AB, in member AB, I would find the force due to these 3 loads. I put that down here. I would find the force in AD due to these 3 loads and put that down here. And I would do that for this column. For FQ, I would analyze all the internal forces due to this load. So I would analyze all these members, find out all their internal forces due to that point load. I would record the lengths of each element. So for example, down here, this was 4 and 4, therefore length AD was 8 meters. And AB is going to be 5 meters, 5, 5, 3, 3. So AB is going to be 5 meters, BC is going to be 5 meters. CD is going to be 6 meters. BD is going to be 5 meters again. Your A and E are constants which are given. A and E are given here. Right, so I'd plug that in. I would multiply everything out. So I would take FP, FQ times L, divide that by AE. I would take this column times this column times this column, divided by this column. Sorry, I didn't realize this is all curved. Divided by this column, put that result in here. This should give you a result that's in millimeters usually. Millimeters, maybe the tens of millimeters if you get very large forces like we have here, but it should be something relatively small. At the very end, I add up everything in this column, and that is my deflection. This deflection is at the point and in the direction of my virtual load. So in other words, if I get a deflection, if I get a value here of 5 millimeters, that would mean that my delta C at the top, my point C would move to the right by 5 millimeters. Right, if I get delta here of 5 millimeters, that means that it's moving to the right by 5 millimeters. If I got a negative deflection here, it would be going to the left. So your sign does matter, your magnitude does matter, and everything is based on what you chose originally. Right, I chose mine going horizontally originally. I chose mine going to the right originally. Therefore, a positive deflection will mean a deflection to the right. So once I have this was just for the horizontal displacement at C. I need to do this again for the vertical displacement at C. So I need to analyze this truss now, right? It's the same exact thing as before, except instead of having it horizontally, I have it vertically. I need to reanalyze this. I create another table, or if you want, you can just add an extra column and an extra column. So 2 extra columns, one for FQ, one for your new product. When you add that up all again, so this was delta C in the X direction, you'll add up in the Y direction, right? So you'll do that again for this one, and you'll do it again also for horizontal deflection at A. So you'll do all this again for this one here. So as you can see, for this relatively simple problem, you already have to analyze 4 separate trusses. There is some degree of symmetry, not symmetry, but like, maybe I shouldn't use the word symmetry, but because you're analyzing the same geometry each time, there is, you can use a lot of your same equations and just change some of the values around. Like your angles will be the same, for example, but it just takes quite a bit of time. As for the SAP 2000 part, you should have enough information to test this on SAP. The only thing that might be an issue is the area. There's a couple different ways to check it. One, you can use SAP 2000 to just make sure that your internal forces are correct. So, in other words, don't worry about the deflection. Just make sure that you manage to get the same internal forces that you got in your hand analysis. I will say that if you use SAP 2000 to check just your internal forces, you still do have to do the work to verify that your forces are correct. At least make sure you analyze the P system by hand. I'll say for now that I guess that's okay for you to generate your Q system by using SAP 2000. But it's very important that you get some practice with this, at least doing this by hand, because you won't have your computer available with you on an exam. So if you do this all in SAP 2000, that's great. But when it comes to the actual exam, if you can't do it by hand, then you're gonna struggle. So please make sure you can at least do this. At least do one truss analysis case by hand. And then you can check the rest of your forces on SAP 2000. SAP is industry grade, so it takes into account a lot of things that we wouldn't normally consider. For example, it takes into account the fact that you're using steel, and there are specific yield points for steel that we don't take into account. We don't, for example, assume that the steel will undergo like bolt tear out, for example, or it won't undergo like block shear. Those are things that we don't take into account in this course. You do take into account with SAP 2000, so SAP might give you very different results for deflection than you generate here. So that's why I'm weary of having you check actual deflections using SAP. Other than that, I will be going into problem 2 next. Problem 2 and problem 1 are very similar. I'll just explain what this extra, how to find what this deflection equals 0 actually means. And yeah, let us know if you have any questions.